right, let's test that understanding. So here we go. We have example, the first one. We have a 1,000 kilogram car that has an engine that can produce a net force of 2,000 newtons on the car. Car needs to go from 10 to 30 meters per second up an on-ramp to enter a freeway. How long does the on-ramp need to be for the car to gain the required speed? Show a solution using forces and motion, and then using work and energy. So this will give us a chance to kind of compare and contrast the difference between these two. But to kind of make it simpler for both of them, I'm going to list out what's given to me. We know the mass is 1,000 kilograms. I'm going to leave off the units to keep it clean. We know our net force equals 2,000 newtons. And we know our initial velocity equals 10 meters per second. And our final velocity equals 30 meters per second. And the question is asking, how long does the ramp need to be? So how long kind of makes you think time, right? But if you read the whole question, how long does the ramp need to be? We figure out that we need the length of the ramp. So that would be our distance that we would need to travel, or displacement. So from here, this is where it's going to branch off into two different ways to solve this problem. So I'm going to first start with forces and motion. So we have initial velocity, final velocity, and a displacement is what we need. Sure would be easy if we had a constant acceleration, because then we could just use constant acceleration equations. Let's get our acceleration. We know that acceleration equals force over mass. Force is 2,000 divided by 1,000, and that's going to give us 2 meters per second squared. So I'm going to add that into my given information, 2 meters per second squared. So now starting velocity, final velocity, acceleration is constant. We're assuming it to be constant. And the displacement. So no time. So let's use the no time equation. Vf squared equals V naught squared plus 2a delta x. Solving for delta x, we get Vf squared minus V naught squared divided by, 2a. And now we can substitute. So for this part, this was our equation that we used, and it'll be different on the other side. Plugging all of that in, final velocity squared is 900 minus 100, so that gives me 800, divided by 2 times 2 is 4, so the length of this ramp needs to be 200 meters. That's one way to do it. Let's check the other. All right. So now, looking at work and energy. We have the mass, we have the force, starting velocities. I'm going to play make-believe here. We don't have the acceleration anymore. That's all we've got. We know that if we have velocities, we have kinetic energy. And we're dealing with force and a displacement. So we can use the bridge between the two of them, between forces and kinetic energy. And that is the work-energy theorem. Work equals our change in kinetic energy. We know that work equals force times displacement equals 1/2 mvf squared minus 1/2 mv naught squared. Be careful here. Remember to square your final velocities. Half of mass is going to be 500 times our final velocity times 900 minus half of our mass is 500 times our initial velocity squared, which is 100, equals force is 2,000 times delta x. We're going to divide 2,000 newtons from each side. But first, let's go through some of this math here. 45 minus did I get that right? 4 zeros, 4 zeros. So, oh, that's just going to give us 1, 2, all right, and then dividing that by that 2,000. So we have delta x equals that huge number, whatever it is, divided by 2,000. Now we have 400 divided by 2, and we have delta x equals 200 meters. Hey, same answer. So, same answer. Two different, very different ways to solve this. So you can pick and choose. Do you want to do the two equations where you have to find your constant acceleration? Probably that's where you're going to be leaning right now. At this point, I'm going to beg you to please get comfortable with the work energy theorem, because this nice equation has combined both of these equations, this whole big, long process that went quicker for me because I know these equations off the top of my head. For you, you may be staring at your equation sheet saying, okay, I have my starting velocity, I have my final velocity, I have my force, and I have my mass. I don't see any equation on there that's going to relate these. So while the thought process here may have seemed easy because I know my physics, because I've done so many practice problems, please, at this point in the year, I want you to start going to this. If you have velocities, use kinetic energy and go from there. And then if you have forces, use forces. Just remember that if displacement is anywhere in that realm of forces, then that is just work. Those are the things that you have to have in your memory. Memorizing facts is not great, but it is going to absolutely help with your problem-solving skills. As long as you know what tools you have to work with, then you know what you can solve. We're going to do the last one in the next video.